Let's look at insertion sort, which is a sorting algorithm that treats the input as two parts, a sorted part and an unsorted part, just like the other two simple sorting algorithms that we look at, selections and bubble. Insertion sort repeatedly inserts the next value from the unsorted part into the correct location in the sorted part. So I know this is kind of verbose, but let's look at the actual algorithms here. I think it will be a lot easier to aid understanding. So just like the other two simple algorithms here, whenever you have a simple algorithm using the exhaustive search process, it calls for two loops, right? So there's actually two loops here. One is your for, right? For loop from 1 through size minus 1. So this is loop number 1. And then the loop number 2 is the while loop, right? From this search. This actually calls for current and current minus 1 and then decrement current, it's doing it backwards. This is loop number 2, right? So this is n. This could be also another n, so over n squared. We'll get into the specifics here, but looking from the outside, let's just assume that we have this buffer. This buffer is an array, and it has the index 0 all the way through n minus 1. So what you have here is an outer loop, right, which is in blue, that goes in this direction, right, from top to bottom, right? So for the very first iterations, this outer loop goes from 0 to 1, right? So insert element, right, 0 to 1. The second outer loop is 0 through 2, right? And then 0 through 3, the third iteration, and the fourth iteration, 0 through 4, all the way through 0 to size minus 1. So this insert element gets called n times, right? So over n right there. So I just assume that so basically let's look at the inner part, right? The insert element, what's going on here. So this entire insert element calls for a start index and end index. So start index is always 0, because what we want to do, let's use a different color here. Let's use red. Let's just assume that our end index at some point is here. Okay, so this is so count, right? Count is going to be here. So this is our count here from the outer loop, right? Which is equal to the n index, okay, in the inner loop. So n index is the inner loop notation and count is the outer loop notations, but they're the same. So let's assume red is here. So what happens is, because insert elements happens from 0, right, through n index. So the red index, it's going to go through this bubble up actions here and doing basically a comparison of the elements that has already been in place and see if this is in the right order, basically doing a pairwise, right? So meanwhile, you have this blued outer loop going down towards n minus 1. You also have your count, which is the inner loop, right? Or in this red part. At this point, let me just make a notations here. The outer loop would have been here actually in this case, right? To allow for this count, right, equal to the n index, and that goes down. So this is essentially what happens. And as you move the all of your outer loop all the way to the bottom, and all of the nodes, right, would have been in the correct, right, order, in the ascending order. Okay. So this is an insertion sort algorithm. I know this kind of it's kind of hard to look at this because you have this more to search, you have finish, right? This thing, but just know that this part, right? This entire part, this while loop from this if loop all the way through at the end of this if right here, this is all that entire loop that we're talking about that goes up this way. And this is the n times, right? The worst case scenario. So anyway, let's move on to the next part to illustrate this is in a diagram. I think it's a lot easier to understand. So this red outer loop is here. Initially, it's set to be 0, right? Location 0. So at the completion of the very first iterations, nothing happens. You have the second iteration, which happens when the two elements are set in blue. And the third iteration on the yellow loop ensures that 3 elements are set, right? And the fourth iteration on the yellow loop ensures that the 4 elements are set, as in they're in the rifle spot. So as you can see, each outer loop guarantees 1, right, plus, right, if that loop number is the ith loop, ith number of element would have been in their rifle spot, right? And as you can see here, if we call the insert element on 10, right? Because count is from 1 to size minus 1, right? So at this point, the very first iteration calls for count equals 1, and that 1 backwards, right, towards that. And that should have been in red, right? This is the second iteration loops here. So this double arrows here represent the second loop, right? Going from this location all the way up. So while you have your blue kind of moves down, your red is always kind of iterating, right, against the levels of the blue back into 0, right? This locations from here to this locations, right? Basically, that's where blue one is. So this ensures that all of the elements, right, are in their rifle spot, but it's doing this one at a time, right? So this is a number of times, right? And then this is also a number of times. Let's move on to the next one. So this is a little different than the bubble sort, because bubble sort says, hey, I'm going to project, if my ith location which is my blue here, right, in this element. What I want to do is my red, right, then goes into basically from this on all the way to here. I want to find the minimum elements. If I do find something, I'm going to insert that. Let's say if I found it right here, I'm going to insert that elements here with this, right? So the blue one moves down and the red one is also moved down, but the red one is getting less and less, right? n-1 plus n-2, so on and so forth, and done. Whereas insertion sort, right, is a little different, because you have this actions where instead of seeing this, let me just clear this part, right? Instead of seeing this, insertion sort says, hey, my outer loop, right, is going to be here, and it's going to move down, right? Meanwhile, my, right, depends where the blue one is. So this red one at this point, it's just gonna go back up, right? Looking for and doing a sorting in place like this. Okay, so this is insertion sort. So the direction of the second one is actually in reverse direction of your the selection sort. Whereas bubble sort is going to be a lot different then, right? Because bubble sort says, hey, I'm going to select one spot, and then we're going to have a bubble of actions that bubbles all the way back up, right? Again, all of these sorting algorithms, compares adjacent elements. And this is really the cost. When you do adjacent elements and this entire, right, array has a number of elements. When you do a pairwise comparisons, you're comparing how many times? n-2 times, right? Because let's say if n is 10, if you do a pairwise, you're always comparing, 2 elements at a time. So number of times you can compare is n-2, right? And that times, the other loop, which is n-1, right? So when you have n-1 times n divided by 2, right, this is O of n squared. So this is another representation of how inefficient, right, this sorting algorithm is. And this sort of comparison applies to all 3 of them, selection, bubble, and insertions. So this is the insertion snapshot. Just like before, you have the sorted part, and then you have the unsorted part, right? So while the sorted part is kind of going down, the unsorted part is getting less and less. Eventually, you get back to the completely sorted part. And this is what we have for insertion sort. You can go to the insertion sort portion of your sort.java, which is available in your modules. And then you can go through this code from beginning to end. And basically, what this is saying, the outer loop here, the 2 loops. This is the first loop, right? And this is the second loop part. Okay. The second part is the insertion elements, right? So the first one is saying, my window, right, where I want you to insert the elements in the rightful spot is always from 0 to count, right? This count is from 0, from 1 through size -1, right? So your window, right, from here to here, this entire window where I want you to do the insertion element is always from 0 to count. Okay, so let me just annotate this using this count. Okay, and then the insertion is going to take your count and 0 as the start index and end index here. Okay, start and end index. So start index is always 0, right? End index is whatever the count is, right? So at this point, and I think I used the blue annotations here, blue could be at here. So basically what that means is when I kick it off into insertion element, that window is from 0 to count, and it's going actually in reverse order because now we're doing, current minus, right? So current is end index. So we're going backwards. So this backward motion goes from here to here and doing a pairwise, right? So checking to see if the currents and it's less than currents -1 at that positions, and if so, then do a swap right here, and then move the currents back into the next one. So you do a next comparisons again. So at some point you're gonna have to stop, right? Because everything would have been in the rightful spot, because you can trust everything is already on top, is already done. So basically, this part is done, this part is done, so there's no more, right? And at some point, more to search is going to be at current index or if does not satisfy this condition, then you get into the else, which is finish equals true. So recall that when you have a more to search and end, right, this end, and then do it finish. Let's say if this part is false, then this entire while loop is basically breaking itself, right? And then you're done, right? This insert element is done. So you only have to go through certain loops in there to see, hey, this is done. Sometimes you may not have to do anything because everything would have been sorted, right? So that would be really nice. Then essentially what you have is just an outer loop, right? Most of the work would not be done here if, let's say, for example, you have a nearly sorted input, right? In this case, hopefully this is clear. If you go down to the sort analysis, as you can see here, just like selection and bubble sort, the general case time is O of n squared, but insertion sort has the best case, which is what I just talked about, right? For nearly sorted inputs. So what does that mean? Well, for sorted or nearly sorted inputs, insertion sort's runtime is actually O of n, which is not printed here, but this is the case, O of n. Why is that? Well, this is n right here, okay? And the reason this is because the insertion element is, actually not doing much, right, in a nearly sorted, which is the best case part. So it could have an array of 100 elements and only 2 of them are not sorted. So that's great, everything else is already sorted and you only have to take care of the other 2. And that, in that case, this insertion element's literally nothing. It will get you to the finish line very quickly. And the outer loop, on the other hand, is always O of n, right? So the O of n is going to dominate over the insert element part in the best case scenario, right? Having nearly sorted list. And that is because as follows, because let's go back. I think it's a lot easier to look at this code. So when you have nearly sorted, basically when this reverse action, right, that goes back up from count to always 0. So this is count, which is the inner loop part. Let's say if this initially what happens is your more to search is always true. So this is always true, okay? And this is not finished. Your value current less than current -1. So you're going back up, right? So at some point, right, there's going to be n number of comparison that you're going to have to go through, but not much. Up to, right, that many if your count is already at the end. But let's say if this is not, right, the case, then what happens? The selection criteria takes you to finish equals true and immediately breaks it out of it. So this is This is the breaking out of the while loop, right? So as you can imagine, like if 90% of your right list elements are already sorted, then this value current less than current minus one, it's always going to be false, right? And that would break this one out of the loop, essentially falling back to this guy, right? So insert element is done, right? In O of one, right? In that comparisons right there. And then the next one up is going to be, count plus plus, right? So this part, right, is inevitable. This part is inevitable. Okay, it's O of n. But this part right here, it's substantially less, right? So we can actually go through the algorithmic analysis here, actually mathematical formulation to prove that this is close to O of one. Okay, it's actually, when I say close to O of one, it's actually a constant times something. So this part is nearly nothing. Now, this applies to the nearly sorted inputs in a selection sort. So selection sort does have an advantage over selections and buffer sorts because insertion sort has this best case scenario, right? So I would, recommend that if you have to go through the unsophisticated sorting algorithms to solve a problem, let's say if you don't know how merge sort, how other quick sort, these are more advanced sorts that we're going to talk about of log n, then you want to go for insertion sort. Okay, that would be the case where you have the best case scenario to give you the maximum O of n, actually the best efficiency out of the other two simple sorting algorithms.